Here's something that should not be possible. You are holding, right now, in the room you're sitting in, a source of physical force that weighs nothing. Zero mass. Not very little, zero. And yet, if you pointed enough of it at a mirror in space, you could move that mirror. You could push a spacecraft across the solar system. You could, in theory, shove a wall hard enough to feel it if you had enough of it and enough patience. We are talking about light. Ordinary light. The stuff coming off the screen you're watching this on right now. Stop for a second and actually think about that, because your instincts are about to get insulted. Every single thing you have ever pushed in your life, a door, a shopping cart, a stalled car on the side of the road, needed mass to do it. Newton's second law lives in your bones before you ever learn it in school. Force requires mass times acceleration. No mass, no momentum. No momentum, no push. That's not just a classroom rule, that's how your entire nervous system predicts the physical world. And light breaks it. Completely. Officially, measurably. So here's the question we're actually answering today, and I want you to sit with it before we go anywhere. How does something with exactly zero mass manage to carry momentum? Real, physical, measurable momentum, and use that momentum to push on matter? If your gut reaction is, that has to be a trick of the language, light must have some tiny hidden mass we just haven't measured yet, you're in good company. That was the leading hypothesis for centuries, and it's wrong. We're going to prove it's wrong, using the same evidence physicists used, and by the end you'll be able to explain this to someone else without hand-waving. Let's set the credibility on the table first, because, trust me, isn't good enough for a claim this strange. This isn't a fringe theory or an internet physics rumor. The push of light on matter, what's formally called radiation pressure, was predicted mathematically in 1862 by James Clerk Maxwell, purely from his equations of electromagnetism, decades before anyone could test it. It was confirmed experimentally in 1901, independently, by two separate teams, Pyotr Lebedev in Russia and Ernest Fox Nichols and Gordon Ferry Hall in the United States. Two labs, two continents, same result. Today, radiation pressure isn't a curiosity buried in a physics textbook. It's an engineering constraint that NASA and other space agencies have to actively calculate for, because sunlight pushes on real spacecraft hard enough to shift their orbits over time if you ignore it. This is not speculative. This is measured, replicated, and used. Now here's the reversal, the path that flips your intuition on its head. You'd assume the story goes, scientists found something moving in space, couldn't explain it, discovered it had mass, mystery solved. That is not what happened. The story goes the opposite direction. Maxwell did the math first. He worked out that electromagnetic waves, which is what light is, carry energy. And that carrying energy through space in a wave necessarily means carrying momentum too, according to his own field equations. He predicted the push before anyone had built an instrument sensitive enough to detect it. He predicted a physical force from pure mathematics, no observation required. And it took the rest of the physics world almost 40 years to catch up and confirm he was right. Think about how audacious that is. He wasn't describing something he saw. He was describing something the equations demanded had to exist. Let's rewind, because to understand how Maxwell got there, you need to understand what light actually is. And I promise this part is more interesting than it sounds. For most of human history, light was assumed to be either a stream of tiny particles, that was Newton's view, or a wave rippling through some invisible medium, which was the competing view held by Christian Huygens and later strengthened by Thomas Young's double-slit experiment in 1801. Both camps had evidence. Both camps thought they'd won. Then Maxwell came along in the 1860s and did something neither camp expected. He showed that electricity and magnetism were two faces of the same phenomenon, and that disturbances in electric and magnetic fields could ripple outward as self-sustaining waves, at a speed that matched the known speed of light almost exactly. Light wasn't a mechanical wave sloshing through some invisible fluid. It was an electromagnetic wave, oscillating electric and magnetic fields, propagating through empty space, carrying energy as they went. And here's the detail that changes everything for our question today. A wave carrying energy through space isn't a passive thing. Maxwell's equations showed that an electromagnetic wave hitting a surface exerts a tiny but very real mechanical pressure on that surface. Not because the wave has mass, because it has momentum, and momentum, when it's absorbed or reflected by something, transfers force. Exactly the way it does in a collision between two billiard balls, except there's no ball here at all, just a wave of pure field energy. I want you to pause and try to guess before I tell you. If light has zero mass, and momentum in the classical world is literally defined as mass times velocity, how does anyone even calculate the momentum of a massless wave? What number goes where the mass used to be? Take a second. Most people guess the answer involves the speed of light, and that instinct is closer than you'd think, but it's not quite the mechanism. The real answer required rewriting momentum from scratch for anything that has no mass at all. Before we get to that answer, it's worth sitting inside the confusion physicists actually lived through, because it wasn't a clean, tidy handoff from one idea to the next. Newton believed light was made of tiny particles he called corpuscles, and he had real evidence for that. Light travels in straight lines and casts sharp shadows, exactly like a stream of particles would. Huygens believed light was a wave, and he had real evidence too. Light bends around obstacles slightly, the way water waves do. For over a century, Newton's authority kept the particle view dominant. Then, in 1801, Thomas Young ran his double-slit experiment, shining light through two narrow slits and watching it produce an interference pattern on a screen behind them. Bands of bright and dark stripes that only make sense if light waves are overlapping and reinforcing or cancelling each other, exactly like ripples on a pond. That result devastated the pure particle view for almost 100 years. Light, it seemed, was settled science, a wave, full stop. Maxwell's 1862 equations seem to close the case permanently, describing light as a wave in the electromagnetic field with no particles involved anywhere in the mathematics. So you can imagine how unwelcome it was when, decades later, evidence started pointing right back toward particles again. This is where Einstein enters the story, and not with relativity in the way you'd expect. In 1905, the same year he published Special Relativity, Einstein also published a paper explaining the photoelectric effect, the observation that shining light on certain metals knocks electrons loose, but only if the light is above a certain frequency, no matter how bright you make dimmer light. That paper is the one that actually won him the Nobel Prize, not relativity. And the explanation required treating light not as a smooth continuous wave, but as discrete packets of energy, what we now call photons. Each photon carries a fixed amount of energy, determined by its frequency, E equals h times f, where h is Planck's constant, and f is the frequency of the light. Now here's where the two ideas, Maxwell's electromagnetic waves and Einstein's photons, snap together into the answer to our whole question. Special relativity gives us the full, general relationship between energy, momentum, and mass. And it is not the simple momentum equals mass times velocity you learned in school. The full relativistic equation is E squared equals mc squared plus pc squared, where E is total energy, m is rest mass, p is momentum, and c is the speed of light. Look at what happens when you plug in 0 for mass. The mc squared term disappears entirely. What's left is E squared equals pc squared, which simplifies down to p equals E divided by c. Read that again, because that equation right there is the entire answer to today's question. Momentum equals energy divided by the speed of light. No mass required anywhere in that formula. A massless particle can carry momentum as long as it carries energy, and light absolutely carries energy. You can feel that energy on your skin every time you stand in the sun. So a photon carrying energy E automatically carries momentum P equals E over c, purely because energy and momentum are linked at a deeper level than mass ever was. Mass turns out to be almost a special case, a shortcut that works for everyday slow objects, not the fundamental rule. There's a second way to arrive at the exact same number, and it's worth walking through because it comes from a completely different direction and lands in the same place, which is usually a good sign in physics that you found something real rather than a coincidence. Combine two things you already know. A photon's energy is E equals h times f from Planck and Einstein, and a wave's frequency times its wavelength always equals its speed, so f equals c over lambda, where lambda is wavelength. Substitute that into p equals E over c, and the c's cancel, leaving p equals h over lambda. Photon momentum equals Planck's constant divided by wavelength. Shorter wavelength, more momentum. Longer wavelength, less momentum. That's why high frequency, short wavelength X-rays and gamma rays hit harder, carry more punch per photon than long, lazy radio waves, even though every single one of them is, without exception, completely massless. A gamma ray and a radio wave are made of the exact same kind of massless particle. The only difference is how much energy, and therefore how much momentum, each individual photon happens to be carrying. This is the misconception I really want to correct here, because almost everyone gets this backwards, including plenty of people who've taken a physics class and half remember it. The common assumption is momentum comes from mass, and anything without mass can't have momentum. That's actually a simplification that only holds true for objects moving much slower than light. The deeper, universally correct rule is that momentum comes from energy in motion. Mass is just one very common way to package energy. Light is energy in motion without the mass packaging at all, and it turns out that's allowed because the universe's actual bookkeeping rule is about energy and momentum together, not mass on its own. So now let's talk about how you prove this isn't just an equation on a chalkboard, how you actually see it, measure it, feel its consequences. This is where Nichols and Hall, and separately Lebedev, come back into the story. In 1901, they built devices called radiometers, small, extraordinarily delicate mirrored vanes suspended on a fine fiber inside a near-total vacuum chamber, so that nothing except light itself could push on them. This detail matters enormously. Earlier, cruder versions of this experiment, including the famous spinning light mill toy you might have seen with black and white vanes in a partial vacuum, actually spin for the wrong reason. Residual air molecules heated unevenly by the light, not radiation pressure directly. To isolate the real effect, you need a near-perfect vacuum and precision mirrors. When Nichols, Hall and Lebedev did that correctly, they measured a real, tiny, but unmistakable deflection, light hitting the mirrored vanes and physically pushing them, at a magnitude that matched Maxwell's 40-year-old prediction almost exactly. Let's go back to Nichols, Hall and Lebedev for a moment, because the actual experimental setup deserves more credit than they built a sensitive scale. What they were fighting against wasn't just a weak force, it was every possible source of false positive that could mimic that force. Heat itself, absorbed unevenly by the vanes, could cause tiny air currents in an imperfect vacuum that would push a suspended vane just as easily as light pressure could, and produce a completely misleading result. That's exactly the trap that had caught earlier experimenters. So Nichols and Hall spent years refining vacuum quality, refining the suspension fiber's sensitivity, and running careful control trials, alternating light exposure on and off, checking that the deflection tracked the light exactly and didn't linger the way a heat effect would. When their numbers came in, they matched Maxwell's 40-year-old prediction to within a small margin of experimental error. Not roughly, not in the right ballpark, but numerically consistent with a theory that had been sitting unconfirmed in a mathematics paper since before either of them were doing physics professionally. That kind of precise agreement between a pure equation and a physical measurement is exactly the kind of evidence that turns a hypothesis into an accepted law. How small is tiny here, so you have a real sense of scale, and this doesn't sound like magic. The radiation pressure of sunlight at Earth's distance from the Sun is about 4.6 micronewtons per square meter on a perfectly absorbing surface, roughly double that on a perfectly reflecting mirror. To put that in human terms, the weight of a single sheet of paper resting on your hand exerts about 100,000 times more force than sunlight does on that same square meter. This is not a force you will ever consciously feel standing outside. But scale that surface area up to the size of a spacecraft, sustain it over months and years with nothing to counteract it in the vacuum of space, and it becomes an engineering-grade force. NASA has had to factor radiation pressure into orbit calculations for satellites since the earliest days of the space program, because ignoring it produces measurable errors in predicted precision over time. Here's a beat I want you to actually engage with instead of just absorbing passively, because you might be thinking of a specific counterexample right now. Solar sail spacecraft, like Japan's Icaros mission or the lightsail projects, which use this exact effect deliberately, catching sunlight on huge reflective sails to propel themselves without fuel. If you already know about those missions, hold that thought, because that's a technology story about harnessing this force, and it deserves its own deep dive. It's not what's answering our physics question today. What we're doing right now is understanding the mechanism itself, the "why is this even possible?" underneath the engineering. So set the spacecraft aside for a second and stay with the raw physics, because there's a piece most people never learn. The mechanism gets even stranger, in a good way, when you ask what happens at the level of a single photon hitting a single electron. This is called Compton scattering, discovered experimentally by Arthur Compton in 1923, and it was actually the decisive piece of evidence that convinced the last skeptics that photons were real, particle-like carriers of momentum, not just a convenient mathematical trick. Compton fired X-ray photons at electrons and measured what came out the other side. If light were purely a wave with no particle-like momentum, the scattered light should keep the exact same wavelength it went in with, just spread in different directions. That is not what Compton found. He found that the scattered X-rays came out with a longer wavelength, meaning lower energy, and the amount of that energy loss depended precisely on the scattering angle, exactly as if the photon were a genuine particle that had collided with the electron and handed over some of its momentum. Like a cue ball transferring momentum to a struck billiard ball. The electron recoiled. The photon lost energy and momentum in a way you could calculate with the exact same conservation laws you'd use for two solid objects colliding. That's about as direct as physical proof gets. Momentum transfer, measured, angle by angle, matching the prediction from treating a massless photon as a genuine momentum-carrying particle. Before we move past Compton, let's make sure you actually feel why this experiment mattered so much. Because it's easy to hear the wavelength got longer and let that slide past without registering how strange that really is. Picture two billiard balls on a table. One is stationary, one comes in fast and clips it at an angle. The moving ball slows down and deflects one way, the ball it struck shoots off the other way. And if you know the masses and the angles, you can predict exactly how much speed each one loses or gains. That's just conservation of momentum, physics you can verify with your own eyes on a pool table. Compton showed that photons and electrons obey that exact same bookkeeping. The photon's energy loss, converted through E equals h times f, showed up as a change in wavelength that depended only on the scattering angle, in a formula Compton derived by treating the photon as a literal particle carrying momentum p equals h over lambda, colliding with an electron the way one solid object collides with another. Before this experiment, you could still argue that photons were a convenient bookkeeping fiction, a way to make certain equations balance without necessarily being real objects with real momentum. After this experiment, that argument was no longer available. A massless thing had been caught on film, transferring real, quantifiable momentum to matter, angle by predictable angle. I want to give you the reality check moment now, the place where we step back and ask what this actually means, beyond the equations. The myth going into this video was that momentum belongs to mass, that stuff with weight is the only thing that can shove other stuff around. The reality is that momentum belongs to energy in motion, full stop, and mass is simply the most familiar costume that energy happens to wear in everyday life. Light strips that costume off entirely and shows you the underlying rule directly. When you understand that, you're not just learning a fact about photons, you're seeing, in the clearest possible example, that the universe's real bookkeeping system runs on energy and momentum, and mass is a derived special case concept, not the fundamental one. That's a genuinely deep shift in how you should picture physical reality, and it's one most people go their whole lives without ever confronting directly. There's a broader lesson buried in that reality check, and I want to name it directly instead of leaving it implied. Almost every impossible physical claim you'll ever run into in science boils down to the same pattern. An intuition built from everyday low-speed, low-energy experience gets applied somewhere it was never designed to work. Your instincts about mass and momentum were trained entirely on billiard balls, cars, and thrown rocks. Objects moving at a tiny fraction of light speed, in a regime where the simplified equation, momentum equals mass times velocity, is an excellent approximation. It's not wrong in that regime, it's just incomplete. Light lives entirely outside that regime, moving at the one speed nothing with mass can ever reach, and the simplified formula quietly breaks down and hands the job over to the fuller relativistic version we walked through earlier. Once you know to look for that pattern, approximation mistaken for absolute law, you'll start noticing it everywhere else in physics too. Let's talk about the human cost of getting this wrong, because this isn't purely academic history. For decades, astronomers trying to track comets couldn't explain why a comet's dust tail always points away from the sun, regardless of which direction the comet itself is traveling. Sometimes the tail even points ahead of the comet's motion, which seems to violate basic intuition about trailing dust. That observation goes back to Johannes Kepler in the early 1600s, who speculated, remarkably, that sunlight itself might be physically pushing the dust outward, centuries before anyone had the mathematics to justify the claim. He was guessing. He didn't have Maxwell's equations, he didn't have relativity, he didn't have Compton's experiment. He just had a strange observation and a hunch that turned out, astonishingly, to be correct in principle. It took roughly 250 years for physics to catch up to what a comet's tail had been demonstrating in plain sight the entire time. Kepler wasn't the only one whose instincts turned out to be quietly ahead of the evidence. When Halley's comet was tracked through its historic appearances, astronomers repeatedly noted the same strange geometry in its tail, always streaming away from the sun, reshaping itself as the comet swung around its orbit, never simply trailing behind like exhaust from a moving car. For a species that had, at that point, no concept of electromagnetic radiation carrying force, that behavior had no available explanation at all. It just sat there in the sky, generation after generation, an open question nobody could close. That's worth pausing on. An answer was visible in the night sky for centuries before the mathematics existed to actually read it. And there's a more recent, more consequential version of getting this wrong. Early spacecraft navigation in the 20th century occasionally showed small, unexplained drift in trajectory, tiny deviations from where Newtonian gravity and standard propulsion calculations said a probe should be. Some of that drift, once engineers accounted properly for solar radiation pressure and even the subtler effect of a spacecraft's own heat radiating asymmetrically off its surfaces, resolved into precisely predictable numbers. Ignore radiation pressure on a multi-year deep space mission, and your predicted position can be off by a margin that actually matters for navigation, for communication windows, for mission success. A force so small you could never feel it on your skin is large enough over the distances and timescales of a spacecraft's journey to require its own line item in the physics of the mission. It's also worth being honest, in the spirit of evidence-first reporting, about where this idea still gets stretched further than the evidence comfortably supports. You'll sometimes see claims online that radiation pressure alone could explain everything from unusual asteroid trajectories to speculative propulsion schemes for interstellar travel, presented as settled fact rather than active, ongoing calculation. The real physics is more measured than that. Radiation pressure is real, precisely quantified, and genuinely useful, but it is also extraordinarily weak per unit area, which is exactly why it took until 1901 to detect directly, and why practical applications like solar sails require enormous, extremely lightweight surface areas to generate anything close to useful thrust. Evidence-based doesn't mean anything involving this effect must be true. It means following the actual measured magnitude of the force wherever it honestly leads, including when that magnitude disappoints a more dramatic headline. So let's bridge this to now, to where this stands today, because the story didn't end with Compton in 1923. Radiation pressure and photon momentum are foundational working physics inside quantum electrodynamics, one of the most rigorously tested theories humanity has ever produced, confirmed to extraordinary precision in particle accelerator experiments. Every time light is described bending around a black hole, every time a laser is used to cool and trap individual atoms down to near absolute zero, using nothing but carefully aimed photon momentum, a real Nobel Prize-winning technique called laser cooling, you are watching the exact same principle we walk through today, doing genuine cutting-edge work. Massless light carrying real momentum, physically nudging matter, precisely enough that physicists now use it as a tool to manipulate individual atoms with a level of control that would have sounded like science fiction to Maxwell in 1862. There's an even more delicate version of this in use today, called optical tweezers, developed by Arthur Ashkin, who won the Nobel Prize in Physics for it in 2018, at 96 years old, making him the oldest Nobel laureate in history at the time. Optical tweezers use tightly focused laser beams to trap and physically move microscopic objects, individual living cells, strands of DNA, even single viruses, suspended in place and dragged around with nothing touching them except the momentum carried by photons. Surgeons and biologists now use light itself as a pair of hands, small enough to manipulate the machinery of life, one photon momentum nudge at a time. That's not a metaphor, that's the literal mechanism running in labs around the world right now, built entirely on the equation P = E/c that Einstein and Maxwell's work made possible more than a century earlier. Before you go, here's the misconception I want you to walk away actively correcting in your own head, because I guarantee you'll hear someone repeat the wrong version eventually, maybe even yourself in a weaker moment. It is not that light has a tiny bit of mass we just can't detect yet. Every precision test of the photon's mass, using everything from laboratory experiments to observations of how radio waves from distant pulsars travel across the galaxy, has placed the upper limit on any possible photon mass at a number so close to zero, down around 10 to the negative 18th electron volts if you want the actual bound, that for every practical and theoretical purpose it is exactly zero. The push you feel, described in the equation P equals E over C, isn't a workaround for a small mass. It's the direct signature of the deeper rule the universe actually runs on. Now here's a question I genuinely want you to sit with, and I mean this. Drop your answer in the comments before you look anything up, because I want to know what your gut says. If a photon has zero mass and travels at the speed of light no matter what, and momentum for a massless particle depends entirely on its energy, what happens to that momentum, to that push, as a photon's energy changes? What happens to radiation pressure for a photon stretched out to a lower frequency by the expansion of the universe itself over cosmic distances measured in billions of light years? That's not a rhetorical flourish. That is a real, unresolved thread we are going to pull on directly in the next file, because it connects everything you just learned about photon momentum to the largest scale physics there is, the stretching of light across the universe, and what that does to the tiny, relentless push it's been carrying since before the Earth existed. If this kind of evidence-first reframing is the reason you keep coming back to this channel, you already know what building a case like this takes. Weeks tracking down the original 1901 papers, cross-checking the Compton scattering numbers, making sure every claim in this script traces back to something verifiable and not just repeated folklore. If you want to help keep that standard up, a super thanks goes directly into the next investigation. Either way, I'll see you in the next file, when we find out what happens to a push that's been traveling for 13 billion years.